Welcome back. I was traveling earlier this week, so sorry, we don't have the exams graded. I know. Yeah, I have a lot. I got back last night at 2 in the morning, so I'll have a lot of grading to do, but anyway. Any questions before we proceed? I'm sorry I'm a little hoarse today. All right, so on Wednesday, you started talking about quantum mechanics in 3 dimensions, right? And I believe you saw how to separate variables into x, y, and z. And you also talked about the hydrogen atom. In the classical picture, the Bohr model, right? I don't know if Professor Kiernan mentioned this classical model, right, where you say, well, angular momentum is quantized, and you get the basic result from quantum mechanics. You get the energy levels, right? He went through that on Wednesday, right? And you've probably seen it before. One thing I always found ironic about that is that's called the Bohr model. And you're supposed to say, oh, boo hiss, the naive Bohr model, that's wrong, and the quantum mechanical model is right. But do you guys know the history of Niels Bohr? He is, as much as anyone, sort of regarded as the father of quantum mechanics. So although that simple model is ascribed to him and has his name attached, and maybe in high school or early college you learn there's this Bohr model and it's wrong, it's completely unfair to Bohr the person because he's actually was the main champion. In fact, he battled with Einstein as to whether quantum mechanics was right. And he had the Bohr school, it was called, not that there was a school called Bohr, but rather he was so influential, he was in Copenhagen, that people from all over Europe came up and studied with him or worked in the institute he was at. And it was called the Bohr School, and they sort of developed the way you should look at quantum mechanics. And they sort of had this intellectual rivalry with Einstein that was very fruitful, because Einstein was sitting there poking holes, good holes in it, and the back and forth sort of strengthened the understanding of everything. But nonetheless, so you saw that, and so now, I mean, why go to the pain of showing you in this class going to 3 dimensions? Well, the answer is because if we want to talk about the atom lives in 3 dimensions, right? So an atom, let's take the simplest possible atom that has a proton and an electron separated by r. There's a potential energy which is just minus e squared over 4 pi epsilon naught 1 over r. So now immediately we run into the problem, which was the kinetic energy is p squared over 2m. And in quantum mechanics, we wanted to turn that into minus h bar squared over 2m. Well, d by dx squared in 1D. And then we said, well, in 3D Cartesian, then this should be, d by dx squared gets replaced by d psi by dx squared gets replaced by just taking the derivative with respect to x squared, then y squared, then z squared. And that's all fine, and you simply separate things that way. But if we have something that depends on r, it's not that simple at all, right? I mean, remember r is unfortunately this, right, by the 3-dimensional version of Pythagoras' theorem, okay? So we can't write, for instance, p squared turns into d by dr squared plus d by d theta squared plus d by dz squared. It's simply uglier than that. And as you should learn in calculus, you may have, well, actually, just a poll. So do you know, how many of you have seen the three-dimensional, maybe you don't know this language, but the three-dimensional Laplacian operator? How many have not? Okay, well, I'm glad some of you have and some of you haven't. So I'm just going to mention it briefly at the beginning of class. And then if you haven't seen it, I'm not really going to attempt to teach it to you. But let's review enough that hopefully it doesn't seem completely alien. In fact, let me just back up, because I do want to motivate it a tad. In 2D, I'm going to go quickly here. This is stuff I think you should have all learned. If I have the r vector in 2D, I can certainly think of things being in x and y, but I can also draw a local coordinate system with an r hat there and a theta hat. Unit vectors in the direction of r and in the direction of theta. Right? And in fact, our hat is this little vector. It's cos theta along the x-axis plus sine theta along the y-axis. Theta hat is minus sine theta along the x-axis plus cos theta along the y-axis. You can sort of see that just by staring at the figure, right? And so, for instance, if I have r, the vector, and then I want to take, r, the vector is r cos theta x hat plus r sine theta y hat. I can also say that r is r times r hat. These are all true. Okay. But taking this form, if I do dr, I could take the differential of r or the differential of theta, and I've got to do both by the chain rule. So this is dr times cos theta x hat plus sine theta y hat. That's taking the derivative of r. Now I have to add a term where I take the derivative of theta. Here r won't change. The derivative of cos theta is minus sine theta d theta x hat plus cos theta d theta y hat. And cos theta x hat plus sine theta y hat is just r hat. Minus sine theta x hat plus cos theta y hat was just theta hat. So this is plus r, that's not a vector, I'm sorry, that's just the magnitude r, plus r, and then there's a d theta both places. And so this is what dr becomes. Is that familiar to you? Right? Anyone for whom that's not familiar? Okay. So just to remind you, so that's the sort of thing we're doing. That's in 2D. Now, okay, that was just looking at a vector r and thinking about the unit vectors. What if I have a function of r? Not r just itself, but r the vector. If I take a differential of that, I have to take the partial with respect to r times dr plus the partial with respect to theta times d theta. That's just, well, I don't have to put the vector symbol in there. That's just the, sorry. That's just the chain rule of calculus. But what's convenient is to write this slightly differently. let's write this that way. I divide by 1 over r and I multiply by r. R d theta is a change in the vector r in the theta direction, and dr is a change in the vector r in the r direction. And then we write this way. Okay? So we define this thing del of f as df dr r hat plus 1 over r df d theta theta hat. That's called the gradient. Okay? And I think you should have seen this in a calculus class. I just wanted to put it in my own words. So if I have a function that depends on r and theta, I think of taking a differential as this one process times the change in the vector. And I'm working in these new coordinates r and theta, and it's not simple. In x, y, z, this thing is just d by dx plus d by dy times x hat and times y hat. And this is just dx hat. This is just dx times x hat plus dy times y hat. But in theta and r, things get a little more complicated. I have 1 over r df d theta. Okay? And this is the way I think of the definition of del, the del operator, the gradient operator. And so if I want to take two derivatives of something, which I need to do because that's sort of what my prescription is, p squared, which I'm going to need for kinetic energy, is two derivatives. For p squared, what I want to do is, it turns out you want to take del dot del of psi, which is to say take the, if it was just Cartesian, you take the x part, this is vectors, and you dot the x part into the x part and the y part into the y part, and it's just what we wrote over there, just what you did on Wednesday. But if it's these coordinates r and theta, I multiply this thing twice, or I multiply that thing twice. Okay, and that, we throw away the vector symbol because this is a dot product. We write del squared of psi, and that's what we're going to deal with. And the full three-dimensional version of del squared of psi in spherical coordinates is messy. The del squared operator is the following. Well, let me first try to write the del operator in 3D, in 3D spherical coordinates. Let me write this down. And just as a reminder, let's draw the three-dimensional coordinate system before I do that. So I have x, y, and z. And I have r. All right. Just to remind you, if you, well, maybe you haven't seen this, I write by convention an angle theta there. Okay? And I take the projection down into the xy plane, and I write phi there. And the z is the simplest thing. Z is the, so if I think of the vector r, it's got x, y, and z components. The z component is straightforward. It's r cos theta, because this is just the angle between the vector and the z-axis. I think you can see that then this projection down into the xy plane is r sine theta. Right? And if this length is r sine theta, then the projection on the x-axis is r sine theta times cos phi, and the projection on the y-axis is r sine theta times sine phi. This is the analogy. Well, actually, I didn't even write it here. X is r cos theta, y is r sine theta. And those two pieces I used to write this. Well, that's r hat. But if I had a full vector r, it's r cos theta, x hat, plus r sine theta, y hat. So this is just completely analogous. This is going to 3 dimensions. And whereas the del operator these are cylindrical coordinates, right? There's also you can have a z-axis that's simple, and is just simple Cartesian properties. So if that's cylindrical coordinates, the spherical del operator is d by dr, just like that, times r hat. Plus 1 over r d by d theta times theta hat, plus 1 over r sine theta d by d phi times phi hat. So that's one derivative. And then, so if I think of the derivative like the momentum in quantum mechanics, p psi in quantum mechanics is going to turn into h bar over I del psi, where that's the derivative operator on psi. I have to write all this stuff down. So it's messy. There's a part in r, which is a simple derivative. There's a derivative in theta, but then I multiply by 1 over r, and then the derivative in phi, I multiply by 1 over r sine theta. And if this just seems like magic to you, just try to think back to this simple, much more sort of concrete example, okay? You know, how these arise. So finally, for the kinetic energy, I'm interested in del squared, which means I'm going to take this, I'm going to square the r part, I'm going to square this part, and I'm going to square that part. Because that, you know, when I take the dot product of this in itself, cross terms will vanish, but I'll have that squared, and that squared. Not exactly squared, right? I'm saying I'm applying that derivative term twice. Okay, so finally, and del squared is sometimes called the Laplacian, which is what I asked you guys if you had seen. So finally, del squared, it's 1 over r squared d by dr of r squared d by dr plus 1 over r squared sine squared, I need lots of room to write this out, I'll write it here, plus 1 over r squared sine theta d by d theta of sine theta d by d theta plus 1 over r squared sine squared theta d squared by d phi squared. And that's what it is, and that's messy, and I'm sorry, and that's just life. It's going to be straightforward, we're going to work with it, but it's messy, and that's just what it is, okay? And realize what this is doing. If I'm going to look at this r part, I'm going to multiply del squared times a function in quantum mechanics times the wave function. That means I stick the wave function here, and first I take the derivative of it, then I multiply that by r squared, and then I take the derivative of the whole thing, okay? So effectively, I'm going to stick the thing I'm going to work on right there or right there. So this derivative of theta is going to have to operate on that and on that, okay? I could have written this out as a term that had a second derivative and a term that had the first derivative. This is just more compact, so people like to write it that way. Okay. So that's where we are, and that's what we have to do. So now let's consider Schrodinger's equation. So I have minus h bar squared over 2m del squared on psi plus u. Now u only depends on radius for an atom with just the Coulomb potential times psi equals E psi. All right. And I'm going to separate variables. So just like you did with x, y, and z, right? When I first introduced the notion of separating variables, just as a reminder, we separated x and time. This equation already had separated x and time. The fact that I went to 3 dimensions doesn't change that. This is the spatial part. There's already a time part, which should multiply any overall wave function to make it the capital psi, which is the full wave function. Now, though, I'm going to separate r, theta, and phi, not x, y, and z, because the potential doesn't break down by x, y, or z. R contains, it's the square root of x squared plus y squared plus z squared. So we'll write this as r of r, capital R of r. I think that's the symbol for capital theta. At least that's how I'm going to write the symbol for capital theta. And capital phi of phi. So those are 3 functions of r and theta and phi. Okay? And I'm going to plug that in. All right? Just to be compact, you can see that if I plug this in, I'm going to divide by psi and multiply by this. I'm going to just rearrange this a tad. Okay. And then what I have to do is I have to take all of this on these. Okay? So let me go ahead and do that. The r part becomes 1 over r squared d by dr of r squared dr dr. There's a 1 over r there from here. The theta and the phi parts weren't acted on by this. They cancel the theta and phi part there. Okay? Plus 1 over r squared sine theta. Now I'm doing the theta terms. D by d theta, sine theta, d capital theta, d theta. And out front there's a 1 over capital theta. Plus, and let me erase all of this. This is all very straightforward. It's just a little messy. Plus 1 over r squared sine squared theta d by d phi squared. And actually, and there's a 1 over capital phi. Let me write it. Let me put it there. All of that is equal to minus 2m over h bar squared e minus u. Now, let me clean this up just a little bit. I've got 1 over little variable r squared running around. So let me erase that and multiply everything by 1 over r squared. I'd rather write it on the other side here. I know you can't do this as nicely in your notes. And we want to use the same sort of argument we used before about if these are independent pieces, each depending on r or theta or phi, then they all have to be constant, right? But I've got to be a little bit careful. It's a little bit more complicated here. It's not more difficult, it's just a little bit more complicated. This term mixes phi and theta, okay? And this term has r. So it's not quite the same. Basically, this term has to be constant, okay? Because it only depends on phi. This term also has to be constant. And the combination of this part, E is a constant, but U depends on R, and I have R there. So this term plus that term together have to be constant, okay? But that's the same argument as before. Those things have to be constant in order for this to make sense. If it's true at one value of R and theta and a whole bunch of values of phi, then this bit, which depends on phi, better end up being constant at the end of the day, right? So it's the same argument we've used before. So this is three equations. This is three equations. One for R, one for theta, and one for phi. And we just have to solve them separately. So let me start solving them. I'm going to work backwards. I'm going to solve this one first, then this one, then that one. Okay? I know this is sort of dry mathematics. But this is important. Realize why was quantum mechanics formulated? It was formulated, wow, there's a lot of reasons it was formulated. I mean, this is the way nature is, so of course ultimately we were going to formulate it if we understood things. But the first understanding that it was there, and of course the main place you see it in its effects is atoms. All right? And so this is the full-blown treatment. I am going to stop. We're not going to thoroughly study this to death like you will do if you take another course in quantum mechanics. This textbook is interesting in that it really does try to show you, though, the real treatment. So we're going to do bits of the real treatment. And this is what underlies chemistry. So when you learned about orbitals and you had these drawings of orbitals, we're getting there, okay? And you're really going to see it. The price is that there's a little bit of algebra involved, okay? But let's just go forward. So all of that was by way of saying, pay attention, this is dry math, but the payoff is big. All right, so the phi part was just that this has to be constant, right? 1 over phi times 2 derivatives of phi with respect to little phi squared is a constant. So I choose a constant. I'm going to choose it to be a negative number. If I choose the second derivative to be a negative number, and I'm normal, and then I've got the 1 over the phi there, that's going to pick oscillatory solutions. Sines and cosines are, complex exponentials, right? I think you've seen that enough by now. And so by convention, we write it this way. We write it as m sub l, where m sub l is some number squared, just to make darn certain we're talking about this being positive, but then there's a negative sign out front. And I think you can see that phi has to be, well, it can be a sine or a cosine, or it can be an e to the I m sub l times phi, plus or minus, right? And if I plug in this, take 2 derivatives, I simply get minus m sub l squared times phi, right? So that clearly just solves that. Right? I don't have to do that, right? At this point, you can see that that's just a solution there, right? Just plugging in. It's going to be a solution. Okay? But I can't just stop there. I have to put this m sub l. And of course, I labeled it that funny way because, as you may know, this is a quantum mechanical number for something about atoms, okay? But for now, it's just a constant. I can't just leave it there, though. This constant can't be anything, right? If this is real physical space, and this is phi, right? So here in, here's my vector, right? So phi is this angle. So here I'm going rotating around in phi. Okay, this is theta, all right? If the function has some value here at phi, I don't know what, it's a psi, it's a wave function, has some value here. Is this value the same as that value? It ought to be, right? What if I go around twice, right? Okay, so I had to have that psi of some value phi, or just not the, well, the overall wave function also, but let me just write this part of it, has to be the same as if mathematically I go around once in the phi angle, or I go backwards, or I go multiple times. And so that's simply to say that, well, if phi is 2 pi, I mean, this is to say that e to the I ml phi plus or minus equals e to the I ml phi plus or minus times e to the plus or minus I ml 2 pi, just plugging in that there and separating into the two terms. If m sub l times 2 pi is just 2 pi, or multiple numbers of 2 pi, then this thing is 1, right? E to the 2 pi is 1, right? Because it's cosine theta plus I sine theta. The sine part would be 0, and the cosine part would be 1. All right? So this simply says ml has to equal 0, or plus or minus 1, or plus or minus 2, etc. So you've seen this sort of thing before when we thought about the first thing we did, when we did the infinite square well, we got these quantization conditions. Here I get a quantization condition once again. Each one is a little different. The reasoning is always a little bit different. Don't just stare at this and think you understood it. Really make sure you thought this one through. The argument's a little more subtle here. The argument was that when I go around once, the overall thing can't change. That's to say ml times 2 pi has to be a multiple of 2 pi. Okay? And then e to the I times 2 pi is always, cosine of 2 pi is 1. But we learned something. Okay? And you might remember, this is the rules you learned in a chemistry class for the m sub l. All right? So that's the phi solution. Very, very simple. And in fact, what we do, by convention, we just do this. We just pick 1 as the normalization, and we don't add the plus and minus solutions. That would effectively be like plane, standing waves in phi. We don't take those, we just take this. I won't rigorously justify why that works out, but that does work out, okay? One thing's interesting, if this is your solution, notice that phi star phi is 1. So the probability for the electron is azimuthally independent. Doesn't depend on where you are in azimuth, okay? This is called the azimuthal angle, right? Now let's look at the theta term. Well, let me work in place here, actually. So things got a little simpler because all of this was just m sub l squared with a negative sign, right? And so now this must be a constant, which we call C. And that's the theta equation, okay? So rewriting that, the theta term is simply 1 over sine theta. I'm going to multiplying through by the, if this plus this is a constant times c, which we call c, then I multiply through by capital theta. Oh, yeah, I multiply through by capital theta. 1 over sine theta, d by d theta, sine theta, d capital theta, d theta, minus ml squared theta equals c times theta. Okay. Yuck. Okay. Yeah.
Where'd the sine squared theta go? Like the ml squared.
Thank you. I knew this was too simple. Yeah, it's that. So that's kind of a yucky equation. We're not going to, we're separate the upper level class from this class. I'm not going to find a general solution for this. How am I going to find a solution to this in general? I'm not going to go through it in a rigorous way, but how would I do it? Once again, guess, right? Now, I'm not just going to guess random stuff, right, obviously. Notice that what I've got in here are powers of sine. Here it's sine to the minus 2. Here's a sine. I'm going to take a derivative of it one time. Another time I'm going to take a derivative there. I'm going to have powers of sine. My solutions are going to be, in general, sine to some power, cosine to some power, which I'll write as L. And that is going to be the L from chemistry, okay? And you, in fact, can approach this in a sort of rigorous way where we write down, well, gee, let's assume it's some arbitrary polynomial addition of different powers of cosines and sines to the L, and we can find a relationship between the L and the C and the M sub L, okay? I'm not going to do that, but I'm going to show you let's just look at how a couple of solutions work out, okay? So it turns out the simplest solution is capital theta is cos theta. This is the simplest solution. So we just guess that and plug in. Let's see what happens if I plug in. Okay? So if I plug it in, I have 1 over sine theta, d by d theta. I'll go ahead and take the derivative here. Derivative of cos theta is minus sine theta, minus sine squared theta, right? Minus m sub L squared cos theta over sine squared theta equals c times cos theta. Okay? The derivative of minus sine squared theta is minus 2 sine theta cos theta. And I've got 1 over sine theta out front. Minus m sub L squared cos theta over sine squared theta equals c cos theta. This sine theta cancels that sine theta. So I have the expression minus 2 cos theta minus m sub L squared, this stuff, equals c cos theta. And here, I went through this, first off, to show I can find a solution, and secondly, to show what typically happens. This will work, but I get a requirement on m sub L and c. This is cos theta, that's cos theta. So if c is this constant, i.e. if c is minus 2, it's okay. This term has cosine in the numerator and sine squared in the denominator. It will never, I don't know what to do with it, but I remember m sub L equals 0 was allowed. It was actually allowed in a trivial way, which I didn't allow for the particle in a box. M sub L equals 0 was just that phi is a constant. So, e to the 0 is 1. That's not that's not like an interesting solution to the particle in a box. But it is reasonable here. It's perfectly reasonable to have like the phi part be nothing, just a constant, because I still have the theta and r parts, which are interesting, okay? So m sub l is a reasonable solution. So m sub l has to be, m sub l equals 0 is a reasonable solution. Okay? So those two things work. And they just, I find that that's what the constants have to be. All right? I would invite you to also try, oh, I don't necessarily want to erase this. It's all right. You could try sine theta. That also works. And you get that c is again minus 2. But then in that case, m sub l is not 0. It's 1. Okay. So, in general, with theta of that form, we get solutions they're the so-called associative Legendre polynomials. They have terms cosine L theta, again, sine L theta, or they'll maybe have a term like cosine L minus 1 theta sine theta. So there's this sort of total power will be L, and it might be either cosine to the L or sine to the L, or it may be cosine to the L minus 1 times sine, or it can be L minus 2, okay? That's not what we're gonna, that's the part I'm just kind of skipping. Why this funny name? Simply because this is sort of just a mathematical problem. What are the solutions to that differential equation? In the 19th century especially, mathematicians were really getting into things like this. Legendre solved a more general form than that, for which this is a special case, which is called associated, and the polynomials in the sense that, right, a polynomial is, a plus bx plus cx squared plus dx, powers of something, but it's a power in sines and cosines, not in just an x, okay? And so he worked out that, and this is a special case of that. And I'll just give a few examples. And then there's rules for the c and the m sub l. And what it turns out is c is always of this form, minus l times l plus 1. So in fact, we don't talk about c, we only talk about l, okay? You saw here that c was minus 2, which came from this being power 1. So it turns out this was c equals 2 was also l equals 1, okay? It's power 1. And 1 times minus 1 times 1 plus 1 is minus 2. Okay? And m sub l, in general, it goes from 0, plus or minus 1, plus or minus 2, etc., up to plus or minus l. And that should look familiar. Okay? And so this result, which you may have learned in a chemistry class, say, if you want to, you can say it has as its foundation is just this result of solving this partial differential equation. Okay, for the simplest possible thing in quantum mechanics, momentum, which is p squared, which becomes the second derivative, and how it works out in 3 dimensions and spherical coordinates. Okay, and you get these rules. Let me just list a few. If L, I'm going to write down, I won't write it here, let me write it here. L, M sub L, and theta. There's the 0, 0 case, where L is 0 and M sub L is 0, and it's just a constant. So when M sub L is 0, this becomes a constant, and it turns out you also get the same idea in theta. It's just a constant, and the overall normalization is 1 over square root of 1 over 4 pi. And that's not an accident, right? That 4 pi is the coefficient for the surface area of a sphere. And if you think about what we're doing here, that had to be the normalization. 1, 0, we just solved. It was cos theta. And it has some normalization, 3 over 4 pi. Okay? But if L is 1, meaning I'm going to take power of cosine or sine, I also had M sub L plus or minus 1. The rules allowed that. I can find that just by plugging and chugging and playing around with these conditions. It's 3 over 8 pi sine theta, as I mentioned. And it has the e to the I term. Depending on whether I take plus or minus 1, I have e to the I plus or minus I phi. Okay? Nope, that's the theta. I wrote theta, I meant phi. There's the 2 case. 2 here, 0 there, 2 for L, 0 for M. This is, can't read my handwriting for the coefficient. It's some coefficient times 3 cosine squared theta minus 1. Again, power of 2, which is reflected in L being 2. There's a 2 plus or minus 1 case, which is some factor here, times cos theta sine theta. E to the I plus or minus I theta, I phi, etc. Dot, 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 right on down the line. It's all very straightforward. This is what they are, okay? So this has been pretty dry mathematically, but in fact, as you probably know, L is intimately related to angular momentum, and we'll explore that next time, okay?